All right. So the first 3D problem I'm going to do is it's going to skip all the stuff with joints. We'll put that aside for the next thing to talk about, but we're just going to do a 3D problem where all the loads are provided already, and you'll see just how to work with a 3D problem. It's basically the same. Okay, so say you got this rectangular solid. And the coordinate system is like this. These lengths, the cross section is a square, so these two lengths are the same. That's 1/2 meter. And then this length is 1 meter. The mass is 60 kilograms. And here are the external loads applied. There are two unknown force components, here and here. I'll call that Rx and Ry. There's a force going this direction that I'll call B. And so those are unknown. Those are like, those are standing in for what are going to be joints later. Those are the unknown like reactions that we'd have to solve for. There's a force vector in the center of the front face that's also unknown, and call that F. And then at the corner where the origin is, there is a component in the positive y direction, I'll call that AY, and a component in the negative z direction, I'll call that AZ. And then there are also two applied couples in the center of the top face. That's what the double arrow, which I assume that originated because that's indicating that it's made up of two forces, but that's how you indicate couples. So a component that's 300 Newton meters and a component this way that's 100 Newton meters. And we want to calculate all those unknown forces. So first, let's just think we haven't seen thought about couples this way yet. So what if there was none of these other loads were here? The only load applied to this thing was this 300 Newton meter couple. What would that, it would produce an angular acceleration. What would that angular acceleration look like? Yeah, exactly. It would follow the right-hand rule with your thumb there, and so it would be spinning around like this. Okay? Any questions about that? What if that wasn't there and the only load was this 100 Newton meter load? What would that be doing? Yeah, it would be rotating like barrel roll. So when couples are indicated that way, it's saying that, and I guess the last thing, how would you represent this couple vector? How would this be represented as a vector? What would be the x component? 100, the y component, 300, and then 0, z. And if this, say if this 300 was pointing down, it would be 100, negative 300, 0. So you read the components of these couples the same way you read vectors. It's just you have to remember that they're a different type of vector. Okay, well I'm gonna say this is good enough as a free body diagram. I'm not going to draw another free body diagram. So let's just go right into the pancake table. Pancake artist, row 4, marzipan. And before I start filling this in, is there anything you can do to, like, what's your first hint about whether or not this is going to be solvable?
How many variables?
Yeah, right. So how many variables do we have here? Let's see, 1, 2, 3, 4, 5, 6. We have 6 variables. So, and we know that Newton's laws are going to give us 6 equations in 3D. So this should be solvable unless some of those are redundant forces. You know, it's still possible that it wouldn't be, but that's a good sign. All right, so let's start with AZ and AY. What are the coordinates of the point where that force is applied? Yep. So this is 3D, so it's going to be 0, 0, 0. About point, we could choose anything. I guess I'll choose the origin again. The row vector, subtract those, and you get 0. So now the force vector, there's no x component, so this is 0, AY, and actually what I'm calling AZ here is pointing in the negative z direction, so call that negative AZ. Take the cross product and you get zeros. Now let's go to this force F. What are the coordinates where that's applied?
0.5, 0.25.
Yeah, 0.5x, 0.25y, and then 0 for z.
Is this one where you can just drop the point down into the 1, 0.0, or 0.5 and 0, 0 along the line?
Yes, you could, right, but I think, yeah, you could move that location anywhere in the z direction. Because it has to be, the line of action is parallel to the z-axis. About point is still zeros. So the row vector is 0.5, 0.25, 0. What's the force vector? 0, 0, negative F. And the cross product, negative 0.25 F, positive 0.5 F, 0. Let's do the weight force next. So what's the location where the weight is applied? It's at the center, yeah, so it's going to be 0.5 in x, 0.25 in y, and then negative 0.25 z. So 0.5, 0.25, negative 0.25. About point is 0. So this is the row vector. The force vector is 0, negative, what did I say the weight is? Okay, so negative 588.6, and then 0z. And I don't have this one written down. Can someone calculate that?
147.15.
Okay.
That's negative. It's positive. Yeah.
And then 0, and then z is positive.
It'll be negative.
It'll be negative, and it's twice this. 2.
294.
It wouldn't be negative.
Negative, sorry.
And that's positive.
X would be negative, because it's double negative.
For the previous model,
Yeah.
for the action, it would be negative 0.25 f, and not just negative 0.25.
F, yes. Okay, so now that's the weight. So now let's go to this force B. What's the location of that force? Yeah, 1, 0, 0. About point is 0, so the row vector is 1, 0, 0. And what's the force vector? Yep, negative b, 0, 0. And the cross product is 0. And you can see that makes sense because the line of action of B goes right through the about point. Anytime the line of action goes through the about point, there can't be a moment. And what do we have left? The one up in the RY and RX. What are the coordinates of that? 1.5 and then negative 0.5, I think. And then about point is 0. Row vector is 1.5. Negative 0.5, and the force vector is Rx, Ry, 0. And if you take that cross product, I believe you get 0.5 Ry, negative 0.5 Rx, and then Ry minus 0.5 Rx. And And we have one load left. That's the known couple. Since it's a couple, we don't care about any of this stuff. And we can just enter this in as positive 100x, positive 300y, 0z. Okay. So now we just have to set up the equations. Newton's second law says zero ay negative az plus 0, 0, negative f plus 0, negative 588.6, 0, plus negative b, 0, 0, boo, plus rx, ry, 0 is equal to 0, 0, 0. And then the rotational equation. Negative 0.25 f, positive 0.5 f, 0. Negative 147.150, negative 294.3. .5 ry, negative 0.5 rx, ry minus 0.5 rx, plus 100, 300, 0 is equal to zeros.
For the 0.5 ry and then negative 0.5 rx moments, it should be positive 0.5 rx and not negative.
Okay, for this one?
Yep.
It's positive, but then remember you have to switch the sign of the y component in the cross product because y is always the weird one. I knew somebody who went to, you know who, is it Gillian or Jillian Anderson from X-Files? I met somebody who went to high school with her, and she said that that my story, my example of like the kind of person that illustrates the y-axis or whatever, that's what that example is based on. She went and spent the summer in England and came back and spoke with a British accent for the rest of high school for like 2 years. Weirdo. All right, so what a mess. I haven't solved this. Okay, so we need 7 columns, 6 rows. There's equation 1, 2, 3, 4, 5, 6. And the variables are AY, AZ, F, B, Rx, and Ry, and then the constants in the 7th column. So in the first equation, we have B's, we have -1, Rx's, we have 1, and everything else is 0. I'm going to just leave all the zeros blank. For the second equation, AY's, we have 1. Ry's, we have 1. And the constant, move it over to the other side, and you get positive 588.6. For the third equations, AZ, we have -1. F, we have -1. Everything else is 0. Fourth equation, F's, we have -0.25. Ry's, we have 0.5. And the constants, we have positive 47.15. Fifth equation, F's, we have 0.5. Our X's, we have -0.5. And constants, we have -300. And the last equation, our Y's, we have 1. Our X's, we have -0.5. And constants, we have 294.3. Okay, so AY equals AZ equals F equals B equals RX and RY. Okay, Vadim, give it to me. Oh, dang. Okay, someone do it, please. Unsolvable.
Damn. But think how mad you'd be if you didn't have a calculator.
Yeah, exactly.
But it shows the process.
That's what I get for doing this example without solving it first. But anyways, the basic approach that you take, you can see, is the same. Just all your vectors are three-dimensional vectors. Your moments, instead of having a single non-zero element, have 3 non-zero components.
I got the,
You did get numbers?
yeah.
Oh, you did?
So basically, this is how I put it,
Mm-hmm.
and this is what I got.
Okay.
So I don't know. I might have put something in wrong because most of them.
How many people got unsolvable?
I got 5 zeros and a 1.
Yeah, 5 zeros and a 1.
All right. Well, we'll just go with. I don't know. Seems likely that I did something that's redundant here and it's unsolvable. All right. Well, so tomorrow I'll start talking about joints for three-dimensional bodies, and we'll be able to do problems like this, but where all of those reaction forces, instead of being the form being given, you've figured them out what they need to be based on the kind of joint it is.